Welcome to AI Dispatch, your channel for the latest AI videos on YouTube. If you don't want to miss these updates, please like, subscribe, and share. Today's video comes from OpenAI. The team demonstrates that GPT-5.2 has already contributed solutions to previously unsolved mathematical problems. Their argument centers on a technical claim. The bottleneck limiting scientific progress isn't computational power or model architecture, but the friction embedded in research workflows. They've built Prism, a context-aware environment designed to collapse the distance between conceptual insight and formal proof. We'll examine how this tool restructures the mechanics of scientific work. The OpenAI team has presented evidence that challenges a long-standing assumption about artificial intelligence, that these systems function merely as text summarizers or code generators. Their position is that certain models have crossed into territory where they contribute to unsolved mathematical research. The technical foundation rests on what they describe as a thinking mode. A physicist in the demonstration didn't ask the system to edit prose. He requested verification of a differential operator calculation and a symmetry check embedded in a draft paper. The model passed the equation directly from the document, performed formal verification, and returned a judgment on mathematical correctness. This workflow represents a departure from treating AI as a writing assistant. The system is being deployed as a verification layer within active research. The team's analysis of capability development contradicts the dominant scaling narrative. The standard position holds that breakthroughs emerge from larger parameter counts and expanded training datasets. OpenAI's researchers argue that for scientific applications, interface design imposes a harder constraint than model size. They reference a parallel from software engineering. Developer productivity increased sharply, not when models improved, but when AI was embedded directly into integrated development environments. The same principle applies to research tooling. Prism auto-loads a scientist's entire project context, eliminating the need to manually upload files or explain background. The value proposition isn't a smarter model. It's a model that operates inside the workspace, removing the overhead of context transfer. This design philosophy directly addresses a specific pain point in academic publishing. Converting hand-drawn diagrams into LaTeX or TIGZ code represents a known friction point. The process typically requires hours of manual adjustment to achieve publication-ready formatting. The demonstration shows a physicist photographing a rough commutative diagram sketched on a whiteboard. The system generates compiled code for that figure within seconds and inserts it into the manuscript. The technical barrier between abstract geometric reasoning and formatted output has been compressed to near zero. The cost of translating conceptual notation into formal syntax has effectively disappeared. The workflow model being proposed departs from serial research processes. Conventional practice involves sequential steps, literature review, mathematical verification, manuscript preparation. Each task waits for the previous one to complete. Prism enables parallel task execution. A scientist can spawn multiple instances of the AI, each holding full project context. One instance conducts a deep literature search, while a second verifies differential equations simultaneously. The researchers describe this as converting individual research labor into a parallelized operation managed by a single investigator. The temporal structure of scientific work is being reorganized from sequential to concurrent. The underlying principle unifying these design choices is friction removal. Every technical decision targets a specific obstacle between initial hypothesis and formal verification. They are systematically eliminating formatting overhead, context switching costs, and sequential dependencies. Their projection is that by 2026, the mechanical aspects of research, code generation, citation management, equation verification will no longer consume meaningful researcher time. What remains is the intellectual core, formulating questions and interpreting results. The implication is that if mechanical barriers vanish, the rate at which new findings emerge may exceed our current capacity to absorb them. If you're interested in the video featured in this episode, click the link below to watch the original.